All right, so this is a review for conservation of energy and energy transformations. Kinetic plus potential energy gives you the total energy or mechanical energy. So the learning targets, conservation of energy, I can define and investigate the law of conservation of energy. I can identify different types of energy transformations, and I can calculate potential energy, which is mass times the force of gravity times the height. Kinetic energy is 0.5 times the mass times the velocity squared, or the velocity times the velocity. So potential and kinetic energy, you often see this in terms of a swing or a pendulum, something falling. It's easiest to demonstrate that. So the law of conservation of energy states that energy cannot be created or destroyed, but it can be transformed from one form to another. Changing the energy from one form to another is referred to as transformation. Energy can be transformed from kinetic to potential energy and from potential to kinetic energy. Since energy cannot be created or destroyed, the amount of energy at the start of the transformation is equal to the amount at the end. We'll be doing some calculations on this, and we'll be discussing that a little bit more with some illustrations. So potential energy is stored energy. So an example, you can see the hammer. It's lifted above the ground. It could very easily break the piggy bank if it's dropped. The higher you raise the hammer, the more potential energy it has. So other examples are fuel for your car, explosives during the 4th of July. Even the food that you eat is stored chemical energy. Coiled spring or pulling back on a bow is due to the state. So something springy, so moving it, stretching it causes a position change. So one thing that we talk a lot about is gravitational potential energy, called Gpe, stored energy due to gravitational attraction between all objects. And it depends on its mass, the gravity. So Earth's gravity is 9.8 meters per second squared. That's the acceleration constant that objects are being pulled at, and height. So if we take a look at this, you have, if we make the height longer, then, or taller, or further from the ground, then the potential energy goes up. So you can see that. So the higher the height, the higher the potential energy. Also, if you make the object larger, the mass gets bigger. So does the gravitational potential energy. So let's calculate gravitational potential energy. So first we need to look at that GPE, gravitational potential energy, is equal to M, stands for mass. So the mass of an object. So M is the mass. The G is the gravitational constant for Earth, 9.8 meters per second squared. And H is the height. So let's look at this diagram here. We've got the mass, kilograms is your unit for mass, and the height is 40 meters. So we're going to do 5 kilograms times 9.8 times 40 meters. And that'll give us a joule. So if we do that, I'm going to use my calculator. I'm going to take 5 times 9.8. And again, it would be different if it was the moon, which is 1.6 times 40. Now I don't have to put the units in. 1900 and, did I do that right? 9.8 times 40. Yeah. 1960 joules. Okay. So that's what that looks like. That's how you calculate those. I got 60. Why did I get 50? All right. 9.8 times 40. Yeah. 5 times 9.8. Yep. So a little discrepancy there. All right, so let's do this one, the gravitational potential energy of a 2.5 kilogram monkey hanging from a tree. So we're, again, hanging, so the force of gravity. So let's do that. We've got 2 point, okay, let's get the pen here. 2.5 times 9.8 for the gravitational potential energy, acceleration due to gravity, and 7 meters. So we're going to end up with joules again. So taking my calculator, 2.5 times 9.8 times 7, 171.5. Straightforward, just multiplication. And you can see the plug and chug that they did. 2.5 times 9.8. They use parentheses to show multiplication times 7. Give you joules. All right, so now let's moving on to kinetic energy. They're interrelated. Remember I said that potential energy can go into kinetic energy, can be transferred or transformed into kinetic energy. So, so kinetic energy, and we're going to use a little different formula here. So in kinetic energy, the greater the speed, the greater the kinetic energy. The greater the mass, the greater the energy. Okay, so what we're going to do in this particular case, so we're going to make this, instead of 1/2, we're going to go 0.5. Same thing, and we just have to multiply. All right, so let's calculate the kinetic energy of this baseball thrown to us. It has, we have to have this in kilograms, so we have 0.15 kilograms. It's thrown 35 meters per second. So what I like to do is I like to show it as 0.5 times the mass times velocity, because a lot of times people think velocity squared is really 2 times 35, and that's not correct. That's not correct. All right, so what I do is I let you put the mass in here, 0.15, and then we're going to go 35 times 35. So that way it gets you in the habit of seeing that squared is that. So we're going to do 0.15 times 35 times 35. I get 183.75. 183.75. All right. See if my, oops, I forgot the 0.5 times 0.5. Yep, 91.87. Yep. So if I go back one, forgot to multiply it by this 0.5. So that's a common mistake. So this is 91.875, 91.875. There we go. Correctamundo. All right. So the cheetah, kinetic energy of a 44 kilogram cheetah running 31 meters per second. Let's calculate this out. So 0.5, that's my 1/2. Mass is 44, so I'm going to multiply that. That's 44. And then I'm going to do 31 times 31. I can use the 31 squared button if you have a graphing calculator, a calculator that has that. 31 squared times 44 times 0.5. I got 21,142 joules. Okay, just rounded it. Okay, so transformation of potential energy to kinetic energy. At the maximum height, the ball has all potential energy and no kinetic energy, right? Because potential energy talks about height, so the maximum height, so that is the furthest away from the ground, so that has all potential energy. It's not moving, so no kinetic energy. As the ball rolls down the hill, some of the potential energy is converted to kinetic energy, right? So yeah, it's starting to speed up. So it's got some kinetic energy and it's reduced its potential energy because the height has gone down, right? So the height it's half as high. So 1/2 is high. So it's lost some height. So if this was 10, this is now 5. And because it's 5, it has less potential energy. It's gained some speed, so it's increasing in kinetic energy. At the bottom of the hill, there's no potential energy, okay? So there's no height. 0 height here, no PE, no PE, like RE. And that has the maximum speed, so it has all kinetic energy. Total mechanical energy is conserved. Potential energy at the top of the hill is equal to kinetic energy at the bottom of the hill. So these numbers, if this was 100 joules up here, total PE, no kinetic and 0 kinetic energy. Down here, it has 0 potential and 100 joules of kinetic energy. So we have all that to contend with. All right, so let's take a look at this. So let's just kind of go this. This is a high diver. Potential energy at the top is 10,000. Kinetic energy is 0 because it's not moving. Starts to speed up. And you'll notice that the potential energy has dropped from 10,000 to 7,500. And the kinetic energy is 2,500. At the halfway point, halfway down, 5,000 equal. They're equal. 5,000 and 5,000 still equals 10,000 because of conservation of energy. 3/4 of the way down, losing height, so we lose potential energy, but we're gaining speed, so we got 7,500 kinetic energy. And then at the bottom, where we have no height, so we have 0 potential energy, but all it is converted to speed. So transforming from one to the other. So if you take a look at this, PE transforms or changes to kinetic energy. So here's a roller coaster ride with some loops. So as the roller coaster goes to the top, all potential energy. And as it comes down, it loses potential energy in red. And then when it goes through the loop, going up, potential energy goes up, but it's also converted to, so let's look at this as kinetic energy. You see the kinetic energy went to 100 when it got to the bottom. Same way here. But the total energy, which is a combination of those two, stays at 100. Now, in real life, we would lose some of this to friction and thermal energy. So the total energy would still be the same, but we'd have another bar in here that would be taking into account thermal energy. All right, so at which point is kinetic energy the greatest? And if you'll notice, Kinetic energy is the greatest at the bottom, B. Right? Okay. And the point of potential energy being the greatest is where its high point at A and C. All right, so if we calculate the potential energy on kinetic energy of the skateboarder, remember, because this is stopped and zero speed, we have potential energy and kinetic energy is equal to zero here, no speed. Now we have a 50 kilogram person, right, at 9, so we're going to use 9.8 meters per second, multiply times 5. So if we do that, 50 times 9.8 times 5, we get 2,450 joules. Okay, so it's all potential energy, 2,450 joules at the top. So from that point on, we can remember at the bottom, we're going to have, it's going to be reversed. Potential energy is going to be 0, but the speed is going to get in there. So the kinetic energy, 2,450 KE. So we can calculate all along the path. So calculate the potential energy. So we were going to say this one would be A, right? This is A. All potential energy, no kinetic energy if it's at the top. Oh, at the bottom, I'm sorry, it says skater at the bottom. So at the bottom, we have 0 potential energy. Cross this out. And 2,450 joules at the bottom because we have all speed, no height. All right, halfway down. So halfway down, you're going to split it. So 2,450 is going to be 1,225 for potential energy. You lost some height and you've gained some speed. So we have D here. All right, so that's as far as I want to go with this. Okay, there is a slide presentation or a quizzes that you can do to show your work on. Thanks for coming in, guys. Appreciate it.